What's going on, my friends? Welcome aboard. Today I'm going to be talking you through these knapsack discussions here. So basically what I have in front of me is 4 different knapsack solutions to the knapsack problem, and what we need to get out of these sessions is the different paradigms, or even like the different algorithms within the same paradigms that you can use to obtain different solutions at the cost of different various running times. And what we're gonna do in this coming 2 or 3 sessions is we're gonna discuss this greedy approach of the knapsack here. It's greedy approach simply because of the logic that it follows. And as you can see, the way, or if you do know what the greedy approach works, or how it works in this instance, it basically sorts the items by oh, by the way, if you don't know what a knapsack problem is, just Google it. It's a very common problem. Just go to Google, type in knapsack problem, and what we're dealing with here is 1 or 0 knapsack problem. We're not dealing with partial problem. So more like an analogy of that would be, let's say a thief intrudes into a house and then finds different things, like finds TVs, laptops, watches, and whatnot. That kind of problem. So you cannot take half of a TV. Either you take a TV or not. So that's the kind of items we are talking about in this knapsack. So yeah, well, for the partial ones, you can have like slight modifications where you are allowed to take, maybe you want to steal sugar or meal, you can take half of it or something like that. But that's not what we're dealing with here. We're dealing with whole objects. And in this solution here, there's a greedy one, as I've said in a minute ago, and I'm gonna take you through exactly how this thing works in a minute. This is just more like a quick rundown of what I have. And then over here we have the dynamic programming solution for it. So as we can look here, we have a very basic recursive solution, and that recursive solution is defined by these base cases here. When the capacity is 0, we return 0. That means you cannot carry anything into your knapsack because your knapsack is full, or something like that. The analogy could also be that you don't have a knapsack. And then another thing, another base condition is that your items, the number of items you're looking at is 0. If you don't have any items, then you cannot take anything, so you get 0. And as you take a look here, we're returning the maximum of either taking an item or leaving an item. Leaving an item is quantified by this recursive definition here. Taking an item is quantified by this recursive one as well here. And we're just obtaining the maximum of this. So this is more or less the base case from which we are building these ones above here. So this one above here is logically the same. You have base cases there, and here if you haven't initialized the memo, you initialize it here and you check if a value has been computed already. If it has been computed, then don't need to recompute it, which is the main difference between these two, is that it caches results into a memo. So you don't need to recompute already computed problems or sub-problems, because you have a lot of overlapping sub-problems in dynamic problems. So this is where the caching comes in. And then lastly, you have these value after computing it, you save it here. Other than that, these two codes are basically identical. And then the final one here, we have the bottom-up approach. The bottom-up is really different from these two. Really, this is one thing. The only difference is that one has a memo and the other one doesn't. The difference between these two is that the bottom-up solution considers first solving the smaller sub-problems first. You start with the smaller problems with hopes that solving the smaller problems will yield solution to the bigger problems at large. And you solve all sub-problems whether you will need them or not. Whereas these bottom-up dynamic solution, it's really bottom-up because you're starting with a larger problem, the whole problem, and you subsequently divide it into smaller pieces, and that is what is meant by top-down approach. And the bottom-up, as I said, you consider the smaller first, and the bottom-up, it solves the solutions on demand, only solve the problems as you need them. And yeah, that can be computationally expensive when you need to resolve the same things, and then it's handled by these memo here. And then what I can tell you off the bat is this is probably the slowest. This is just the normal dynamic one. It's the slowest, but it's the easiest to think of or to come up with. And this is the slowest. This is probably the second slowest. This will probably be the fastest of the dynamic. And this is probably not as fast as the greedy solution here. And these greedy solution, let me just quickly run you through here. I'm using the systems performance library here. As you can see, I'm getting the performance from the performance hook here. I'm not even using the performance observer. This is just a quick sketch for you just to get a rough estimate. If you need to use the performance observer, you can go ahead and use it. But over here, I'm just concerned about just the raw numbers itself. And this is not a scientific document. I'm just taking you through what measures you can follow through. And then let me just quickly run you through how much computation each one takes. That code is literally here. I'm just gonna stop this now. I'm using Yarn to run my program. As you can see, these one took full second. First of all, the greedy one took very small time. By the way, they all came up with the same solution. 42619 all came up with 42619, having given the same inputs. But this one here, the greedy is significantly faster, no question. It's this one here. But the bottom up, you can see it came second best, the memo came third best, and just the basic one here, it was the least fast. But yeah, so I'll take you through that in the next round, and hopefully this will be a very helpful journey for you. You know, you can benefit some techniques which you can employ in your own solutions along the way. And I'll see you guys in the next one, where we'll be discussing about the greedy approach, and then hopefully you guys will benefit one or two things from there. Otherwise, this is Juba signing out. I'm your host. I will see you in the next one. Cheers, guys. Have a good one. Happy coding. If you didn't know, now you know.